So welcome everyone to our last seminar of the WRRC fall series. And I just wanted to thank you all for being here during the busy holidays and during finals. So this week, Dr. Jinyong Liu will be talking about per and polyfluoroalkyl substances. And now I'll go ahead and let Tao introduce our speaker.
This is Tao Yan. I'm a professor in Civil and Environmental Engineering and the Water Resource Research Center at UH Manila. Today, it's indeed my pleasure to introduce our speaker, Dr. Jinyong Liu. I have known Jinyong for several years since I had a research interest in PFAS biodegradation, and he's been working on PFAS chemical degradation. So he came to Hawaii several years ago, and we had some really interesting discussion. So this time he indicated that he's interested in coming to Hawaii for vacation again. So I asked if he's willing to share his research. He kindly agreed, which is really timely for us. As you all know that, right now we are faced with some major groundwater contamination issues, and PFAS is one of them that could be in the groundwater. And Professor Liu has been at UC Riverside since 2016. So they have a chemical and environmental engineering department there. And his research focus is on PFAS degradation, catalytic reduction of oxidants, and also transition metal chemistry. So I have been following his research in recent years, and he's really has established himself as a leading figure in the chemical degradation of PFAS. So without further ado, I'll let Jinyong talk about his research.
Okay, thank you everyone, especially for Dr. Yan's kind invitation for me. So let me start my presentation, and can still everyone hear me?
Yes.
Okay, nice. So good afternoon, everyone. Today I'm going to give a short talk about my recent research on the PFAS degradation, and especially we focus on the structure-reactivity relationships and treatment strategies. Let me start. Okay, so the key points for today's presentation will include the following aspects. The first, I want to give some brief background of the PFAS and the pollution issues, and then I will move on to our discoveries on the structure-reactivity relationships, especially how we understand and predict oxidative and reductive degradation for a wide scope of the PFAS pollutants. Then I will also talk about our treatment strategies toward the complete defluorination of a lot of the PFAS pollutants. And I also want to highlight why we say PFAS is not forever chemicals, although many news media said PFAS is forever chemical, but we have a different opinion. So first, let me start from the background of the PFAS pollutant. On the left side of the screen, you can see a summary that is published in 2014, summarizing the major categories of the PFAS pollutants that has already been detected in the environment. So if we check the details, we can see that the PFAS can be into such as the fluorocarboxylic acid. We can see the carboxylic acid functional group there. And the chain can be very short, such as we have 4 carbons fluorinated, or it can be very long, such as 14. So these are in the series of the fluorocarboxylic acid. They can be long and short, but they have the same and functional group. And
Dr. Liu, your audio is kind of interrupted right now.
Phosphoric acid, many other configurations.
Oh, there we go.
And then we also have some ether compound. We also have the derived precursors with the different structures, and they can be built into the surfactants, such as what you can see on the right side. So we actually are looking at more complicated structures, but actually they are not complicated at all if we check the structural details. So all of these structures on the right side are from the aqueous film forming foam that is used for the firefighting. So we can see that the organic structures are so diverse, but if we check the details, we can see that on the first three, they are actually carboxylic acid derived, because what we see is that the link between the fluoroalkyl group and the organic group are achieved by the amide linker. So if this kind of surfactant get hydrolyzed, we're going to have the carboxylic acid remain, and that need us to treat. And the second category is called the fluorotelomer derived. What we can see is that between the organic structure and the fluoroalkyl chain, we have some linkers just as the pure hydrocarbon. So we see this hydrocarbons between the fluoroalkyl group and the organic group. And the third category is sulfonic acid derived. What we see here is sulfonamide, and sulfonamide can be hydrolyzed into sulfonate. And then we have to deal with the perfluorosulfonic structure. So where do we see the PFAS pollution? So here we can see the yellow sticky solution that is actually the aqueous film forming foam for the firefighting. And this one is a typical structure of one kind of surfactant. And this kind of surfactant can form the foam for sure. But why we have the perfluoro groups in the surfactant? That's because the perfluoroalkyl chain can prevent the hydrocarbon vapor getting to the air. So if we can generate a foam blanket over the fuel or the hydrocarbon, it can actually separate the air and completely put out the fire in a very short time. This is why the PFAS containing firefighting foams has been widely used for the real firefighting and also the training. And especially for the training, you can see the picture here that a giant amount of foam can be applied and then just leave on the ground and let them slowly sip into the underground water. And this picture shown here is actually the real accident released from some domestic airport just because their firefighting system got some issue and the foams got out of the airport. And the other major source for the PFAS pollution is from the consumer products, because we know the non-sticky pan, and we also know the food packaging materials will have a coating on the surface to prevent the oil penetrating the paper-based materials. And the other big area for the application is fabrics. We have the water-resistant clothes, coating, or even the carpet. They have a layer of the PFAS. So all of these products will finally go to the landfill where the organic bases will be decomposed and release the PFAS into the groundwater and finally become our nightmare for the drinking water safety. So in order to deal with the PFAS pollution, actually we have already the practical technical solutions. If we are going to just purify the drinking water, we already have three options: carbon absorption, ion exchange, and membrane filtration. And they are pretty effective, I would say. But after we apply these removal steps, we are going to face new challenges, such as how do we treat the enriched PFAS in the spent carbon or the spent resin or the nanofiltration or reverse osmosis reject. The second question is how to treat the groundwater with contamination with a high firefighting foams, and the landfill leachate also contains concentrated PFAS. The third question is how do we treat the wastewater from the fluorochemical related industry, because we want to eliminate the contamination at the source instead of doing the remediation. And the last question is regarding the sustainability, because we know that we can just say we should ban the PFAS, but we actually find out that it's so difficult, especially for some special industries such as semiconductor industry. The complete removal of the PFAS from their production process will not do anything good for the manufacturing, so that we have to live with the PFAS for some time. Then the question is how can we minimize or eventually eliminate the future PFAS pollution, or at least make the treatment easier if we cannot completely ban the use of the PFAS. So with these questions, we have already seen a lot of reports regarding the homogeneous or the heterogeneous treatment of the PFAS or the destruction of PFAS. So if the reaction occurs in the solution, we call that the homogeneous process that can involve oxidation or reduction. And if we through some materials, solid materials such as photocatalyst or electrode, or we apply the sonication or plasma or some high energy irradiation, we call it the heterogeneous process. But the majority of the past research have been primarily focused on the legacy C8, PFOA, and the PFOS. And the reason is the US EPA announced the plans to work on these two structures in 2016. So a lot of researchers just follow the regulation or the potential regulation saying that the EPA is only interested in these two structures. So we are working on these two structures. But the reality is, as we have learned, there are so many different PFAS structures, and the scope of the monitoring and regulation will be broader and broader. So it should be a wise choice that we start looking at all of the possible PFAS structures from right now, instead of just focusing on these C8 compound. And later we realize, oh, some structures are even more difficult to treat. Then all of the previous efforts in just treating the C8 will be wasted, because we might have to treat the contaminated water one more time. So this is the highlight of our research, that we focus on a wide collection of the PFAS structures. And another thing I really want to highlight here is that we have recently seen some reports saying the biological degradation of the PFAS is promising, but to the best of my knowledge, the biological degradation has shown very limited efficacy, and we still need some time to see if those reports are really promising or still have some issues there. And but when we go back to the destruction using the chemical and materials approach, we want to set the clear treatment goal that we want to achieve the complete defluorination. So in history for the environmental remediation, we have seen so many examples that people only looked at the disappearance of the parent compound, such as organic contaminant. But in the case of the PFAS treatment, I would say that the disappearance of the parent PFAS does not necessarily indicate an adequate degradation, because we know the toxicity comes from the carbon fluorine bond. And if we want to say the treatment is complete, we really need to make sure all of the carbon fluorine bond has been cleaved. So the definition for the defluorination is the cleavage of the carbon fluorine bonds into the fluoride ion by any mechanism or the pathway. So far, we have known at least two different pathways. One is reductive. So we can convert the carbon fluorine bond into the carbon hydrogen bond, and this process really needs to consume some electrons. And the second approach is oxidative. We want to convert the carbon fluorine bond into CO2 or carbonate based on the solution pH. So either way, as long as we can cut the carbon fluorine bond, and as long as we can cut all of the carbon fluorine bond, we will call that the successful treatment. And we can permanently eliminate any future concerns about anything left for the future work. So if we want to evaluate the system, we typically use the defluorination percentage, or sometimes I say the defluorination ratio, which is just the ratio of how much fluoride ion you can measure in the solution after the treatment, divided by the total fluorine in the initial PFAS contaminant, multiplied by 100%. Then we can get this defluorination percentage. And the ideal situation is we want to get 100%. If you see some technology only report 10% or 50% defluorination, that means incomplete treatment. So then let's move on to what we have discovered so far. So in my lab, we mainly focus on the use of the hydrated electrons, which is so-called a super powerful reducing agent. So the hydrated electron can be considered as a free electron surrounded by some water molecules in the aqueous solution. And this species can be generated from the 254 nanometer UV irradiation on aqueous sulfide. So we know 254 nanometer UV has been widely adopted in the water treatment plant. So it should be an accessible and practical solution if we can play with this system very well. And the hydrated electrons has been shown to enable reductive defluorination. For example, if we want to convert one carbon fluorine bond into one carbon hydrogen bond, what we need to provide is a proton plus 2 hydrated electrons so that the equation can be balanced. But only knowing this reaction itself is not enough, because what I'm going to show you is that the actual defluorination highly depend on the specific structure of the PFAS pollutant. We're going to see a series of very interesting results that not all of the PFAS compounds can be treated in the same way to the same efficiency. So our experimental settings, I would say, are pretty simple, practical, and effective. So here is the initial reaction conditions between 2017, where when we started the real experiments, until maybe 2019 or 2020. So we used the classic reaction conditions that typically involve 25 micromolar of the PFAS and 10 millimolar of the sulfide as a source of the hydrogen electron, and 5 millimolar of the bicarbonate as a buffer. We maintain the pH at 9.5. Why? Because a lot of previous reports using hydrogen electron system, they used the pH 9.5, and we want to make some comparison. So we also used 9.5. And we maintain the temperature at 20 degrees C by the cooling water. And the typical volume is 600 milliliter. This is the real reactor we use in the lab. And we use a 254 nanometer UV in the middle of the reactor so that we pour the 600 ml of solution between the glass wall and also the quartz immersed well that contain the UV lamp in the middle. So what we actually have done in our lab is a series of this kind of reactors wrapped with aluminum foil to prevent the UV leaking. And because we are dealing with a large number of the PFAS compounds, we have a total of 10 of this kind of reactors, and so that we can produce the data in a timely manner. And for the basic characterization of the defluorination reactions, what we use is the mass spectrometry to monitor the parent PFAS compound decay. And also we use electrode to measure the fluoride ion release. And we also monitor the transformation product. And we also conducted some theoretical calculations through the collaboration with the experts. So what we have done so far is we just look at the individual PFAS families, such as carboxylates, sulfonates, and the telomers, and sometimes the ether compound, and sometimes the alternatives with some hydrogens or other heteroatoms in the perfluoroalkyl chain. So here I just want to show you some most essential results. So in these two figures, you are actually seeing the degradation of the parent on the left and also the defluorination percentage on the right. So we have a collection of 10 different perfluorocarboxylic acid from the very short chain to the very long chain. And in general, you can see that they can disappear within 12 hours. And the majority of the PFAS compounds give a defluorination ratio between 50% and 60%. But if we want to compare with the N-terminal functional group, in this case, perfluoroalkyl chain and carboxylate are directly linked. And in the second case, there are some separations, and we call this fluorotelomers because there are some hydrocarbons separating the fluoroalkyl chain and carboxylate. So if we want to compare these two groups, we can find the very obvious difference that in the second case, the fluorotelomers showed very clear and strong dependence on the chain lengths. Only if we have the long chain structure such as n equals to 8, we can achieve some obvious degradation and obvious defluorination. So that means the direct link between the perfluoroalkyl chain and the carboxylate will avoid the dependence on the chain lengths, as we can see in the first case, because no matter if they're long or short, they are following very similar profile. But in the second case, it's different. And then we also compared the degradation between the perfluorocarboxylic acid, the same picture you just saw in the previous slide, and also sulfonate. So in the case of sulfonate, we also see the strong chain length dependence, n equals to 8 gives some good results. And if we have the very short chain like n equals to 1 and 4, basically there's no degradation and there's no defluorination. So the carboxylate and sulfonate have very different results. And if we also want to compare the telomers and sulfonates, we can see the clear difference that even if we work with n equals to 8, the longest telomers and sulfonate, we can tell that the sulfonate is better than the fluorotelomers. So all of these above results show that it's very important to look at the functional group to predict and understand their degradation behavior. So not all of the PFAS compounds we send in the system can be effectively degraded. So that's the first biggest discovery we have seen so far. And with the transformation product analysis and theoretical calculations, we can probe some critical mechanistic insights. For example, on this slide, you see some transformation product we observed from the degradation of the PFOA under the UVisulfite treatment. So we can see the red dot is the degradation of the parent PFOA, but at the same time, we see some product with some fluorines replaced by the hydrogen showing up and down, but this is obviously much more recalcitrant than the PFOA. And we can also see that the 2 fluorines can be replaced by the 2 hydrogen, and they have the tendency of building up in the system. And at the same time, we also see that the PFHPA, which is just 1 carbon less or 1 CF2 missing from the parent PFOA, can also show up at the very beginning and started to quickly degrade. So at least we see 2 different pathways. One is we can have the hydrogen fluorine exchange. The other one is we can have the chain getting shorter and shorter. At the same time, the theoretical calculation can tell us more information about the reactivity of the PFAS, such as on the left side, we can see that the first 3 structures are fluorotelomers because we see this annoying hydrocarbons here. And we use a color code to indicate which one is weak, which one is strong regarding the CF bond energies. We can see that if we have the long fluoroalkyl chain, such as the number C, we can see some green bonds in the middle, meaning they are the weakest bond, and the most probable reactions can start from here. But in the case of the perfluorocarboxylic acid, we can see that as long as we have the direct link between the fluoroalkyl chain and the carboxylate, we have the alpha location showing the very weak bond dissociation energy. And this is completely different in the first case, that if we do not have the direct link, this alpha location CF bond is strong. But if they are next to the carboxylate, they are weak. Okay, so the other experiment we have done, the simulation, is if we impose an electron to the PFAS molecules and we want to optimize the structure to see what happens. In the case of the perfluorocarboxylic acid, we see the spontaneous cleavage of the fluorine on the alpha location. And that's consistent from what we calculated here. But in the case of the fluorotelomers, well, the alpha location is not weak. So what we can see is a spontaneous cleavage of the carbon fluorine bond in the middle. And that's also consistent with what we calculated here. And in the case of the sulfonate, what we can see is upon reaction with the hydrogen electron, we see the spontaneous cleavage of the carbon sulfur group. So that means the sulfonic acid can leave the molecule. So these are some preliminary understanding from doing the theoretical calculation. Then another highlight of our research is that because we are dealing with so many different PFAS structures, we're not only looking at the PFOA or the PFAS degradation. So all of the proposed mechanisms will have more evidence or supports from the similar structure, such as what I just showed you regarding the 2 separate mechanisms with the hydrogen fluorine exchange or the chain shortening can also be seen from the PFDA, NaOA, and HPA. So they have very different chain lengths, but you can see the profiles for the product production and even the time dependence and the trend are exactly the same. So that actually provides a strong and solid confirmation of what we propose. So now I want to show you the quick mechanism regarding how we interpret the defluorination of the PFAS molecule. So if the PFAS pollutant are the perfluorocarboxylic acid, as you can see here, what we just learned is a chain shortening process that after each step, we will get shorter and shorter perfluorocarboxylate, finally into the trifluoroacetic acid and finally into the CO2. So that will be the ideal defluorination pathway. And what's happening here is that initially we know there's a carboxylate group here, and it can do some decarboxylation, although the detailed mechanism are still mysterious, but we are pretty sure the CO2 or the carboxylate group leaves, and leaving the perfluoral radicals here. And then it can get into the perfluoroalcohol, but this one is not stable. As long as you have the OH and fluorine attached to the same carbon, there will be the automatic elimination and giving the acyl fluoride. After another round of the hydrolysis, we can get the carboxylic acid. But this process, we just lose one CF2 in the process. And if we keep this reaction going on, we can finally get trifluoroacetic acid. And this one can also do the decarboxylation, forming the trifluoromethanol, which is not stable, and give you thorough defluorination. But what we also know is that from our previous experiment, we don't see the 100% defluorination. We can only achieve up to 60%. So what happens there is that we also notice there are the HF exchange reactions, right? And according to calculation, we know exactly where they occur, because we know for this kind of structure, the alpha location will have this hydrogen replacing the fluorine. And after 2 steps, now we are actually having some fluorotelomer structures because the hydrocarbon is separating the fluoroalkyl chain and the carboxylate. And in this case, well, we know that when we have the separation, the only possible reaction is that if the chain is long, it will have some weak bond in the middle, so that it might have some further defluorination. But if this kind of structure is already short, then there's no more chance for the defluorination. So that this is why we see the partial defluorination, not the complete defluorination. Okay, so that's the fate for the perfluorocarboxylic acid transformation. But what about sulfonic acid and fluorotelomers? Well, according to calculation, we can compare how long the fluoroalkyl chain is. If the chain is long, we're going to see some weak CF bond in the middle. It can have the exchange and give us very limited defluorination. But at the same time, from the calculation, we know the carbon-sulfur bond can be cleaved. Then the sulfonate can get into this cycle, and then that will follow the degradation pathway of the perfluorocarboxylic acid. So these are the general degradation mechanism we propose for the 3 categories: carboxylate, sulfonate, and telomers. So after going through the details, we can review the experimental data one more time. Okay, so here is our calculation results. We know the carboxylic acid will have some weak bond in the alpha location. So all of the structures will have this kind of weak bond, so that they will follow very similar degradation profile. And also their defluorination is similar. But in case of the telomers, we don't have this special help from the alpha location. Only when you have the strong chain, long chain, you're going to see the weak bond, and that will allow the degradation. As you can see here, only the strong ones will show you some partial defluorination, right? So to this point, we have elucidated why we can see so different degradation profiles for different categories. But still, we have the remaining challenges, because the reason for us to do the research is not just publishing this kind of result without giving a solution. We still have the challenges of the slow kinetics, because you can see the degradation will need at least 12 hours or 48 hours. These are not good. And also the incomplete defluorination, as I have already mentioned. The third challenge is if we have the short chain fluorotelomers and sulfonates, as we can see here, or the very limited or no defluorination here and here. So these are the highly recalcitrant contaminants. How do we deal with that? So with these challenges, we step further into how do we improve the treatment system. The first thing we have done is that we further advanced the UVisulfite system to enhance the kinetics and defluorination simply by raising the solution pH from the widely adopted 9.5 to 12. And how do we do that? we just add some sodium hydroxide to raise the pH, but now you can see the difference is huge. Okay, so at pH 9.5, 24 hours, we have limited defluorination percentage. Now you can see at pH 12, 8 hours, we have substantially higher defluorination. And regarding the degradation of the parent compound, if we model the reaction with first order model, we can see that the K value for at pH 12 is substantially higher, like 10 times faster. And faster reaction and deeper reaction actually indicate the energy saving and also the chemical saving. So previously, people just say that the UV technology is not possible to be used because the electrical energy consumption is so high. But here we just bring down the EE/O, which means the electrical energy consumption upon 90% of the parent pollutant degradation. We bring down this value from hundreds into below 20. And people always set the some threshold that below 20 is good and above 20 is not possible. So we achieve this goal. And what happens there? So I can use this cartoon to give you some general information that at pH 9.5, if we turn on the UVisulfite system, maybe the hydrogen electron is able to cleave 1, 2, and 3 carbon fluorine bond. But if we raise the pH at 12, then the hydrogen electron will have higher reactivity that can cleave extra carbon fluorine bond here. But also the decarboxylation, which is a preferred pathway at pH 12, is also enhanced. So we have two directions, both enhanced by just increasing the pH from 9.5 to 12. And we actually didn't know why the previous studies didn't try the pH 12 and what's the barrier for them to do so. We're not clear, but when we do this, we actually see the substantial increase. But still, raising the pH to 12 just can solve the challenge in treating the perfluorocarboxylic acid, but it still cannot solve the challenges from the short chain sulfonates and the fluorotelomers. So on the left side, you can see the poor performance of the UVisulfite system at pH 9.5. We say that the PFAS is fine, but PFBS with only 4 fluorocarbon chain, the performance is very poor, right? And if we increase the pH to 12, well, it get improved, but still not satisfying. So we see that the PFAS can be shortened, the degradation from 48 hours to 8 hours. This is very good. For the PFBS, well, now we see deeper degradation, but after 8 hours, the reaction is getting very slow. We have to add additional spikes of the sulfide to further push the reaction forward. And the same can be seen that in terms of the defluorination, we also need to add the sulfide for 3 times to push the reaction forward. And this is obviously not so good. And regarding the telomers, we also see the similar challenge. At pH 9.5, we know for the shorter chains, they're basically not working, okay? But at pH 12, we see everything get a little enhanced, but still we cannot tolerate or accept the results. After turning on the UV lamp for 24 hours, we get 10% defluorination. That's still very poor. So we have to do something else to improve this situation. So then we followed this motivation and started adding the iodide. When we add the iodide into the UVisulfite system, we can further accelerate the reaction for 3 to 4 folds, such as you can see here. The blue line is a traditional UVisulfite at pH 12, and the green line is only just that we add some iodide to accelerate the reaction. Now we can see that for the PFBS, the very recalcitrant structure, 24 hours is good. And regarding the defluorination, we can increase from 40% to about 80%. So because we are optimizing the system with a very recalcitrant PFBS, then after optimizing the system, we use the same reaction conditions to deal with the easier compounds, such as the longer sulfonates. Well, they get very nice results, very quick degradation, and significant defluorination for almost 90%. So that means we can substantially accelerate the reaction. And we can see the new comparison matrix. So now we can lower the EE/O, the energy consumption for 90% parent compound decay, from 20 to below 1. So I would highlight this because this has been the lowest number that has been ever been reported in terms of the PFAS treatment, the lowest energy so far. But also, as I want to highlight that 90% of the parent compound removal is not enough, because that means 10% is still remaining in the solution. And we know the PFAS regulation level is typically very, very low. So if you say we still have 10% of the initial pollutants in the water, that's not acceptable. And second, as I mentioned at the very beginning, our goal is to achieve complete defluorination instead of just let the parent compound disappear. So we create another matrix called the EE max defluorination, which means the electrical energy consumed when we see the maximum defluorination has been reached. So that's the end point of applying the UV technology. And we can see here that for the carboxylic acid, they're still below 20. So reaching the maximum defluorination will obviously take longer time than just for 90% parent compound disappearance. But I would say all of these values has been the lowest or without any other technology to compare at this moment, because many other methods haven't done this. They haven't looked into the maximizing the defluorination. So we have some explanation on why the iodide can accelerate the reaction, but we have limited amount of time. I can go this very quickly. That we know the UV irradiation on sulfide or iodide can generate hydrogen electron, okay? But they have different quantum yield or the efficiency. And after the iodide release the hydrogen electron, it will form some other species. We call that reactive iodine species, and they can capture the electron. So that means iodide generates the electron, but then it will turn into something else to catch the electron back. And this actually slow down the reaction. But the addition of the sulfide can capture these RIS so that they have no chance to quench the hydrogen electron. And we have some experimental evidence showing that the combined use of the sulfide and iodide really both increase the concentration of the hydrogen electron and also increase the lifetime of the hydrogen electron. So this is the explanation. We also use the same approach to explain why the higher pH can give the better performance, because we know the hydrogen electron can be also quenched by the proton. Then we can imagine that as long as we increase the solution pH, the proton concentration will be lowered so that we can have the better reactivity. And this is true. This is our experimental data. We can see that at higher pH, we have the longer lifetime of the hydrogen electrons. So another benefit of using both sulfide and iodide is that it can enhance the sulfide utilization. If you still remember, we conducted most of the experiments previously using the 25 micromolar concentration, but we add 10 millimolar of the sulfide. So why we have to restrict ourselves at this low concentration? Because if we increase the concentration for 10 times, well, the defluorination efficiency, especially for the long chain structures, will be lower. That means sulfide is not enough. But we know sulfide is in large excess. So where are they going? So actually, they're wasted by some other side reactions. But as long as we add sulfide, well, if we want to treat 10 millimolar of sulfide, just a one-time addition, without any further addition, we can achieve very high defluorination ratio, already 80% or more. But if we don't add iodide, we will see that the defluorination will get slower. You have to add another spike of the sulfide. You're actually wasting more sulfide, but you're not achieving the best result. So what we see here is that iodide and sulfide work together very well so that they can accelerate the reaction and also increase the utilization of the chemicals. So here you can see that we have done some tests that we add many different PFAS into a brine solution, the concentrated sodium chloride. So they have different structures, the concentrations according to some literature reports. So after turning on the UV sulfide iodide system, we can achieve the majority of them with higher than 99% removal. And we also have about 91% defluorination if we keep the UV for 12 hours. So that means a successful treatment of the potential real samples containing multiple structures in high concentration. So the last question is that, can we achieve complete defluorination? Just now you can see that we can accelerate the reaction by adding the iodide. We can make the reaction faster. So you can see that we don't have to wait for that long to reach the maximum. But still, the maximum defluorination for these two systems are the same. So the iodide can make the reaction faster, but not make the defluorination deeper. And why is that? According to the calculation, as long as we introduce more hydrogens, because we're doing the reductive defluorination, if we add more and more hydrocarbons in the molecule, the carbon fluorine bond will become stronger and stronger, and finally reach some threshold that the hydrogen electron, no matter how we optimize the system, has no way to cleave them through the reductive pathway. But at the same time, the good thing for us is that because we are building or introducing the carbon hydrogen bonds, so these bonds will actually allow the classic advanced oxidation with hydroxyl radical. Well, this might provide some opportunity that if we just use a traditional advanced oxidation, as long as something can be attached here, as long as we introduce some OH into the fluorinated carbon, it will not be stable and collapse and release the fluoride. So what we do here is that, okay, if we want to deal with perfluorocarboxylate or sulfonate, we can first do the reduction using hydrogen electron. And after that, we follow with the oxidation with hydroxyl radical. And how do we do that? We just use the heat to activate persulfate. And under alkaline conditions, we can have hydroxyl radical produced. And how do we, what result do we achieve? Well, you can see that if we apply the reduction, just as what you see before, they can give you substantial defluorination, but not complete. If you follow the second step of oxidation, they reach the 100% for the majority of the structure. So we can achieve near 100% defluorination from these two structures, as long as you have some UV or you have some pressure cooker or something to heat the solution. Then you can just do this at garage to achieve the complete destruction of the PFAS. But in case of the fluorotelomers, we know that these are very annoying. They will substantially decrease the efficiency for the UV system. So what we do here is that we can first apply some oxidation to get rid of these hydrocarbons, then follow with reduction and then oxidation, 3 steps, okay? And this is the result, that first oxidation can release some fluoride, second reduction, and third. Now the majority of them reach the 100% defluorination. So to this point that you can see, we have achieved 100% defluorination for the majority of the PFAS compounds just by integrating the UV technology and some heat to generate the hydroxyl radicals. So the major findings I have shown you is that we see the strong dependence on the PFAS structure. That means we really need to look into the structure and determine the mechanisms and how to improve the system, pH adjustment, and adding the iodide. And we show that the integration of redox process can achieve complete defluorination. So the engineering implication is that first, we really need to deal with all of the PFAS structures instead of focusing 1 or 2. And we can understand and predict the mechanisms for a wide scope of legacy and emerging PFAS. Third one is, I hope my results can convince you that the PFAS is not forever chemicals, because you can just use a common approach, UV and heating, and common chemicals, sulfide, hydroxide, and iodide, without any exotic species or the nano materials approach or any other things that you can achieve this goal, and with limited energy consumption. So our results can benefit from developing more treatment technologies, because we don't have to necessarily use a pressure cooker to heat to generate the hydroxy radical. We can also use electrochemical or many other approaches to do the oxidation. And regarding the environmental monitoring, so if not all of the places have the mass spec, and we also know that mass spec cannot quantify many things, but our approach has already shown that if we just play with the UV lamp and pressurize the cooker, we can achieve almost the complete defluorination, so that maybe we can monitor the total organic fluorine by destroying them into the fluoride ion. And the fluoride ion measurement is easy. Okay, so these are the information I want to deliver today, but because we have very limited amount of time, I cannot go through all of the details. If you have the interest in the technical details, you can check our publications, and this one is pending in revision. And we also touched other alternative structures like the ether compounds, where the molecule contains some other atoms. You can also check our publications. And finally, acknowledgement to my students, funding agency, and all of the audience here. So right now I'm ready to answer your questions. Thank you very much.
Okay, thank you so much for that talk. Let's see. So does anyone have any questions?
Hey, Jinyong, first of all, really nice talk. So I had a question about the pH benefits. You seem to, I think you have data to support that the hydrogen function of your aqueous oxygen is a factor. But have you thought about the production of aqueous oxygen? Aqueous electron? Will pH affect that kinetic process?
Oh, so you mean the pH effect on the production of the hydrogen electron?
Yeah, aqueous electron.
Okay, so regarding this aspect, I would say that for some species, they are dependent on the pH, such as the sulfide. Because we know the sulfide, you can still see my screen, right?
Yeah.
So the sulfide will have some, let me see. Okay, so the sulfide has some pKa that it can be turned into the bisulfide form. So the bisulfide is a poor electron donor, but you really need to remove the hydrogen from the sulfide. You need to expose SO3 minus in the solution. But the pKa for that is only 7. So that means as long as you bring the pH above 8, it should give you the same efficiency of generating the hydrogen electron. But so when we see the difference above the pH 8, for example, between 8, 9, 10, 11, 12, I would just attribute that to the quenching by the protons. Okay. And if we're working with iodide, I would say the iodide will be available to release the electron at any pH as long as the pH is higher than 1. Because iodide is strong acid, the hydrogen iodide.
Okay, so another question I had is, so it seems, the UVisulfite plus iodide really worked so well. How did you, did you have to go through a set of screening to identify sulfite, or have you tried some other anions that might also work?
Oh, okay. So this is a very good question. We are not the first one developed the UVisulfite. So the brief history is that some researchers have done the UVisulfite system to treat the chlorinated organics back in 2012. Then,
Jinyong.
Yes.
So my question was, you were talking about the UVisulfite history, and then we lost you at the point you talked about the chlorinated compounds.
Oh, okay. So for the chlorinated compound, right?
Yeah.
Yeah. So the UVisulfite system was first reported in 2012. Someone reported that to deal with a chlorinated compound, and then some other people followed that to put the PFOA into the system. And they also report UV sulfide works with PFOA, but that direction just get discontinued since 2014. And I don't know why. And regarding the use of iodide, it was even earlier, back in 2009. So we also see some reports using the UV iodide, but that is not as good as UV sulfide. So we focus on the UV sulfide because it has some advantage, such as you don't need to remove the oxygen. So if you want to use UV iodide, you really need to completely remove the oxygen. Otherwise, the performance will be very poor. But in case of the UV sulfide, the addition of sulfide will instantly eliminate the dissolved oxygen, so that you can just operate everything in the air and then pour that into the closed system with a UV lamp. And then you turn on the UV, you get a very nice performance without any nitrogen sparging or something to remove the dissolved oxygen. So we focus on the sulfide for this advantage, and also sulfide is very cheap.
I see. So sulfide basically function as a reducing agents for your system.
Right.
All right. And that's all my questions. Thanks.
Thank you.
Okay, yeah, just wanted to say thank you to Dr. Liu for joining us and for giving the talk today. It was really interesting.
Yeah, if anyone have more questions, you can send me email, and I'm more than happy to answer them.
Yeah, absolutely. Okay, for everyone else who's still here, once again, thank you all for joining us, and hope to see you for our spring semester seminar whenever we get that all arranged and set that up. And I'd like to invite Tom to give any closing remarks.
Thank you. Yes, great talk, Dr. Liu. Thank you very much. Couldn't be more timely. We're in the middle of the biggest water contamination crisis since I've been here, which is a long time. And this topic of degradation of contaminants has come up, and also, you know, the use of the AFFF is part of the story in this particular contamination episode. So it's not directly in the contamination, but the system that delivers it was involved in the pathway. I also want to thank Carrie for doing a great job this semester in running these seminars and organizing the seminar series. I also like to thank Aurora Kagawa Viviani, who worked with Carrie to arrange these great talks, including the one today. And behind the scenes, I want to thank April Kam and Pat Hirakawa for taking care of all the logistics and making sure, you know, these Zoom meetings go well, and they've done a great job. So thanks everybody. All of the people who joined today, look for us next semester. We hope to have, you know, a similarly great lineup of speakers, and we hope you can continue to join us for the spring semester seminars. So thanks everybody.